Okay, I should be recording. This is a quick review of chapter 1 for differential equations. And by the end of chapter 1, we should understand what a differential equation is. We should be able to classify differential equations by order, linearity, and type, and then identify initial value and boundary value problems. We're going to start with what is a differential equation. A differential equation is an equation that contains at least one derivative. These two equations are both examples of a differential equation. The first one, the derivative of y with respect to x is equal to 3x squared. Notice you have a first derivative there. This is a first order equation. It's also linear. It's also non-homogeneous. The second equation, you have the second derivative of y with respect to t plus 4 times the derivative of y with respect to t plus 3y equals 0. There you have a second derivative. You also have a first derivative term, but that second derivative term makes it second order. And this is linear because the dependent variable terms are all linear. The second derivative of y, first derivative of y times 4, and then 3 times y. Those are all linear. And this is homogeneous because we don't have a term that just contains a constant or just contains the independent variable t, other than 0. So terminology, order is the highest derivative that's involved. Linearity is the equation linear in the dependent variable and its derivatives. So there you're looking at the dependent variable for linearity. And homogeneity should be here too. An equation is homogeneous if it contains, if every term in the equation contains the dependent variable. If you have a term that contains the independent variable only, then it's non-homogeneous. Autonomous versus non-autonomous. A differential equation is autonomous if, let me put my pen on. If you can write the derivative in terms of a function of the dependent variable, then it's autonomous. Otherwise, if the derivative is equal to a function of x and y, both x and y, then it's non-autonomous. Or basically, if you can't write the derivative in terms of just the function of the dependent variable. And then explicit versus implicit solutions. And explicit solution means that you could solve y as a function of x, or you can solve for the dependent variable as a function of the independent variable. And then an implicit solution means that really that you don't have the equation solved for y. So you have a function of x and y equals 0 or equals a constant, is how you would write an implicit solution. So here's an example. We're given the second derivative of y plus y is equal to sine of x. Notice that the order is 2. It's second order because you have a second derivative. The linearity, this is linear because y double prime is linear and y is linear. You look at the dependent variables for linearity. And then homogeneity, this is non-homogeneous. Because you have that function of x by itself. When you solve equations, generally when we're finding a solution to a differential equation, we'll solve first to get the general solution. A general solution is typically a family of solutions with that arbitrary constant, the constant of integration. So you might have a plus c, or you might have c times something. The particular solution you can solve for if you're given initial values or boundary values. So it's a specific member of this family of solutions that's found by applying initial conditions or other conditions that you're given. So for example, here I have a differential equation. The derivative of y with respect to x is 2x. I'm going to rewrite that. And I have this one because it's a really simple first order equation. Derivative of y with respect to x is 2x. So you've got a derivative equal to 2x. And how do you undo a derivative? To undo a derivative, you can apply the antiderivative or the integral. And we want to apply the integral with respect to x on both sides. So that on the left side, when you integrate the derivative of y with respect to x, you get just y on the left side. On the right side, when you integrate 2x, you get 2x squared divided by 2, which is x squared. And then you have your constant of integration plus c. So dy over dx equals 2x has a solution of y equals x squared plus c. This is our general solution. It gives you a family of solutions depending upon what that value of c is. C is any constant. Now, if I'm given this condition that y of 1 is equal to 5, I'm able to solve for c. So if y of 1 equals 5, that tells me that when x is equal to 1, y is equal to 5. And I'll substitute into my equation to get 5 equals 1 squared plus c, or 5 equals 1 plus c. Subtract 1 from both sides, and you get c is equal to 4. So we know the value of c is 4 at the point 1, 5, and that gives us the solution y equals x squared plus 4. C is 4. This is our particular solution. A particular solution is going to be one of the solutions in our family of solutions that we get from the general solution. Okay, so initial values and boundary values. A lot of times we'll be given initial values. Initial values are values for the function at one point. So here, if I'm given y of 0 equals 3, and then y prime of 0 equals 1, notice that for both of these values, we're looking at the same value for x. X is 0. When x is 0, y is 3. When x is 0, y prime is 1. A boundary value problem uses 2 or more points. And you have boundary value problems for second order or higher ODEs, ordinary differential equations. So for example, if I'm given y of 1 equals 5, and then y of 4 is 2, in this first point, we have x is 1. In that second point, we have x is 4. So we're looking at 2 different points on the coordinate plane. X is 1, x equals 4. So if I look at this equation, y double prime plus 4y equals 0, y of 0 equals 2, and y of pi equals 0. Is this an initial value problem, or is this a boundary value problem? So remember, initial value problems, you're looking at the same x value for those pieces of information that they give you. For a boundary value problem, the x values will be different. In this first point, x is 0. In the second point, x is pi. 2 different values of x tells you that it's a boundary value problem. This is a second order linear ODE. It happens to be homogeneous. Second order because you have a second derivative. It's linear because y double prime is linear. 4 times y is linear. Is homogeneous because you don't have any terms that are functions of x if x is your independent variable. And that's it. So those are the key concepts for chapter 1. And I will finish up this lecture and get it posted for you. If you do have questions over any specific problems, make sure that you ask.